Okay, hi guys, here's a video for 13.3 in the book. And I'm going to go a little bit fast because this is more of a derivation. It's not something you're going to need to be able to do. So it's to show you kind of where it comes from. And it'll help you with the ideas and the concepts you do need to know. So I've got a mass. We'll just make it a horizontal mass on a frictionless surface. It could be a hanging mass. From a vertical spring, it doesn't really matter because it's still simple harmonic motion even if it's a hanging vertical spring. So if I use the energy equation, conservation of energy equation, we should get, I'm going to pick, say here, where it's, we'd say we pull it out to some distance. Sorry. So if I were to, pull it over here, some initial position from the x equals 0. So here's the x equals 0. That's the relaxed length of the spring. If I squish it to the amplitude, this is going to be the amplitude. I took the mass from here, moved it to the left, and now I'm going to let go. So it wasn't moving, it had no kinetic energy, but it did have spring potential energy. No work is done. And at any given point, anywhere along this oscillation, this is like the homework, 1/2 mv squared, 1/2 k delta x squared, where delta x final. So this position there. All right. So if the book just goes through this and it solves for v final, and that's the equation at the end of 13.2. And I told you before, I think I would memorize that equation, but we are going to use it. We're going to say, well, these are multiplied by each other, this parentheses times this, so I can make the square root of these two different things multiplied together. It's plus or minus, but this here, whether it's plus or minus, k is a constant, m is a constant, so it's just some constant. The final speed would be some constant here, whatever the constant is. It's going to be root k over m plus or minus. Well, the speed wouldn't be, if this is speed, it's just plus. There's really no, this is speed anyway, up here, so no minus. They put a minus in the book, I think. But we get an equation of this form. And then, if you watched the video of the tape on the bike tire that I made and posted, let's imagine you've got something rotating at a constant angular velocity, and it could be on the edge. Everybody puts it on the edge. It doesn't have to be at the edge. Just some spot. It's going to rotate here. And I drew this. So I'm just worried about this spot here. So this circle does not have to be the edge of the disc or wheel. It just needs to be some spot is moving. And our radius here is a. So a is equal to r, or that distance and that distance are both the radius. They're both a. And then if you look at the x position, so this thing is rotated from there to there. Its x position is this distance. Its y position is this distance. And this is kind of for later, but I'll make another video. But just real quick, I'm going to say, look, hey, x is, if you make this angle in there theta, x is a, which is the hypotenuse, cosine of theta. But theta keeps changing because this thing is rotating, right? So theta is really a function of time. But we know how theta is a function of time because if it's constant velocity, I could have written this as, this is coming from constant velocity would be like delta x over t. This is delta omega over t. So omega is omega initial plus, theta is a function of time. Is theta naught plus omega times t. If you just solve this is kind of like theta final, if you will. And if we call the initial angle 0, wherever it is, whatever this spot, let's just make this an angle of 0 initially, then we will have x of t is a cosine theta, but theta is a function of time, and we're going to plug in, this is 0. We're going to make that 0, so omega t. So a cosine omega t, but we'll come back to this idea later. So let's move on here. That's kind of this is kind of 13.4. So we're going to look at instead the velocity. So I drew a bigger picture here. This one was too small. So I've got this spot that's rotating here. This is its tangential velocity. Right here it's going straight up, but over here it's going that way. And if this is the angle that it has rotated through, and then I drew this perpendicular, this is x again, this is y, but this angle here is complementary to that angle there, because this is a right triangle. But this is a right angle, and this up here, these angles must be complementary because they need to add up to 90, because this whole thing is 180, and this is 90, so they have to be complementary. So this angle is complementary to that angle, and this angle is complementary to that angle, so that angle must be theta. And then I want Vx. All right, Vx is going to be Vt, V tangential sine of theta. So Vx is Vt sine theta, but sine theta is also y over a, where y is, if you solved for y, it would be, like, use the Pythagorean theorem and solve for y. You get y squared equals a squared minus x squared, and square root both sides. You get this. And you might be wondering, why do we care? Well, the reason we care is because we're going to plug in sine theta there. And Vx is Vt over a. So there, sorry, Vx is Vt sine theta, but sine theta, we're just going to take this and plug it in right there for sine theta. And we get this. And then this right here is just some constant times a squared minus x squared. And then if we go back to my other side up here, that's what we had. These equations are very similar. Okay, so the V final, the mass moving back and forth, there is the same similar form of equation as the velocity here. It's moving back and forth, so this x position of this thing as it rotates. We could have picked the y position, actually. The y position would just be going up and down and up and down. That's what I did in the video, because it was easier to do use the sun and have a shadow moving up and down rather than left and right. I could have done left and right. But the x position or the y position has a similar form as something in simple harmonic motion. So I just wrote down here, so the x, or we could have done the y, component of a point rotating at a constant angular velocity is also moving like it's in simple harmonic motion. And hopefully you see that from the video with the shadow, but this equation and this equation we're saying have the same form. So the velocity at any point has the same form as simple harmonic motion, so this must be like simple harmonic motion. So why do we care? We already did rotating stuff. Well, we care right now because if these guys are similar, an object's rotating, its x position is similar to this guy's x position as it goes back and forth, then, I'll drop my paper here, we can use the rotating object actually to tell us about our simple harmonic motion, because we know more actually about our rotating object than we do about our simple harmonic motion. So we're going to continue on this side over here. Sorry, it was already there. And already down there. So the equation for the period should be similar. We're going to find how long does it take for this thing to go around once. We can figure that out. And say, well, the equation for this going around, that the time it takes, the equation for the time for the period, and we're not really going to worry about the spot going around. We're going to pretend like it's just going like this, just its x position, right? It's going. It's going fastest in the middle, slows down, fast, slow, right? This going back and forth, left and right, is like simple harmonic motion of the mass. So we can find the period of this pretty easily. The trying to adjust here. The velocity of this, the tangential velocity of this object going around in a circle, we could say that when it goes around once, it's gone 2 pi r in a certain amount of time, but r is really a. Sorry, so r is really a. So we say 2 pi a over some time, but that time is called the period, the time it takes to go around once. And just solving for the period, we get 2 pi a over vt. But here's the deal. We don't really want vt because vt is not the direction we want. We don't want this velocity. We want the velocity in the x, because only the x component, or we could have chosen the y component, only its part of the velocity is simple harmonic motion. So we got to get some way to get to Vx. So actually what the book does is it says, well, let's worry about just Vmax. When is this moving the fastest? So this is kind of a weird proof to me, but this is how you prove the equation we want without calculus. So Vt is equal to Vx max when this object is straight up here, when it's all the way up there at that location, it's rotated to the top of the circle, it's going to be moving all to the left, and its Vmax, just in speed, will be Vt. Okay, so I'm not sure I want to add that to my picture here, but when it's way up here, it will be going straight to the left, and Vt would be, so I'm pretending to write here, draw an arrow, Vt would be Vx. And that's the fastest it's going. We already proved that when it's at the, or we didn't prove that. Sorry, that was for simple harmonic motion. But you see that's the fastest when Vx is going to be when it's up there or down here. So Vx max will be equal to Vt. And then we're just going to plug in here for Vt is Vx max. So why are we doing this? Well, we're trying to get a equation for the period of this thing. And the equation for the period of the simple harmonic motion should be a similar form as this. Okay, so we have 2 pi a. We can do that from our picture, 2 pi times whatever the amplitude is. But what is Vx max? We never got that. So we need to find Vx max for the simple harmonic motion. And then once we get that, it will allow us to use our equation over here. Will allow us to use this equation down there. Okay, so let's go back over here. What's Vmax, Vx max? Well, if we use the energy equation, I redrew the picture here. I did not redraw the picture, sorry. So looking at this picture, the total energy, if we pull it over here, is 1/2 ka squared. And at any given moment, this is the equation from above, the x velocity is only moving, the object's only moving the x, and this is the final situation, plus the kinetic energy plus the spring potential energy will make the total energy, but we're going to make this be 0, so delta x is 0. We're back at the equilibrium, sorry, the relaxed length. So the mass is here, that's when it's going the fastest. And so we just get 1/2 ka squared equals 1/2 mv squared. And we solve that for Vmax. Get rid of the 2 1/2s, divide both sides by m and square root. And now we're going to say, okay, we have Vx max, and we have Vx max down there. So we're just going to plug Vx max is that. And instead of calling it this, we'll just take out the a squared. So root k over m times a. So actually, the way the book solves it is it divides both sides. It divides both sides by Vx max, and then this goes to the other side, and it gets divided. We're dividing both sides by this, and we get this relationship. So t, if you remember from the period, was 2 pi a Vx max. We'll take this all the way. So you're using this equation here. We're going to plug in a over Vx max. So a over Vx max is root m over k. So it says since the x component of the disk is also in simple harmonic motion, this equation should be the same form as for the rotating disk, should be the same as the simple harmonic motion period. And so we're going to say a over Vx max is m over k. So here is the period of a mass on a spring in simple harmonic motion. The period is 2 pi times the square root of m over k. You do not need to be able to derive this, you just need to be able to use it. And then the last thing we're going to say is frequency is revolutions per second, omega is radians per second. So if this were like 5 revolutions per second, this would be 10 pi radians per second. So this is the equation between them, and I'll show you next time this. But if you use this relationship 2 pi, the frequency is 1 over the period. If you plug in that period, you can get the angular velocity is actually root k over m for an object vibrating in simple harmonic motion, a mass on a spring.